guys, this is going to talk about the history of the atomic structure, and as well as we're going to talk about the scientists that made their contributions. You will need to know each scientist, what they proposed, if it was true. If it was not true, you'd be able to tell us why it was not true. That's the whole purpose of this video here. So let's get into it. First off, what is an atom? It is the smallest substance that we can have that will still retain all the features of that substance. It is the basic unit of matter and the fundamental unit of chemistry. It's called the periodic table of elements. You could call it the periodic table of atoms if you wanted to. And it's funny because this model right here is not the right model, and we'll figure out who discussed that and why later. But John Dalton is your first guy. He made the most propositions. So let's go through his 5 propositions. He said that all elements are composed of very small particles which are indivisible. That sounds good, except for that last part. So this one is not true because they are not indivisible. We already know by now, being the 21st century, that we can split an atom. The second thing he proposed is that all atoms of the same elements are identical. That sounds good, but it's also not true because they are not identical. They do something called isotopes. It's the same element with different masses. We talk more about isotopes later on, but they have a different number of neutrons, so they're not all the same. Number 3, he proposed that atoms of different elements are different. That sounds so right, it has to be right, and it is. Number 4, atoms of different elements can combine with each other, but only in simple whole number ratios to form compounds. That sounds good, and yeah. So number 5, chemical reactions occur when atoms are separated, joined, or arranged. However, atoms of one element are not changed into atoms of another element by chemical reaction. We know that that does happen with a nuclear reaction, but this is chemistry, not nuclear chemistry, so that is correct under the assumption that we understand nuclear reactions. So those are his 5. You do need to know each one, and need to know that number 1 is wrong because they're not indivisible. Number 2 is wrong because they're not identical, because those isotopes exist. Okay, the next guy, J.J. Thompson. What did he discover? He discovered that electrons are negatively charged. He did that with the cathode ray experiment. And this little thing flickering over here is a cathode ray, and I'm going to talk about that in just a bit. But what was his proposition, and was it true? His proposition was that electrons are negatively charged. It was true, and here's the actual proposition. They're lightweight. They still have a mass, even though it's almost negligible, so it's still considered matter because it has that mass. And it's that small mass of proton and neutrons. So we know that electrons are substantially smaller than the inside of the nucleus, the protons and neutrons. So how did the cathode ray experiment work? Well, this little purple beam, you can see it's pointing to it, is the electron stream applied without the magnetic field. The yellow part that's flashing is when the magnetic field is on. But you see between flashes that that purple stream is a straight line all the way through, and it hits right here in the middle of the cathode ray when the magnetic field is not on. Then the magnetic field gets turned on, and you have the positive end up here and the negative end down here. We know by now that opposites attract, so we see when the magnetic field is turned on that it forms that line up top after it's been turned on. And since it's going to the positive end, we know that it has to be negative. That's how this works. You need to be able to explain it to me just like that. The electrons were attracted to the positive end of the magnetic field, telling us that electrons are negatively charged. That's what I want you to write down. That's what I want you to be able to regurgitate to me and explain how this cathode tube array works. All right. He also had another proposition. I know you guys have heard this before. It's called the Plum pudding model. And I'm not going to write this down because I want you guys to write this, what I'm about to say, in your own terms that helps you understand it, because I know you've heard it about 3 different times from 3 different people. But basically you see that it's all separated out. The positive charges are separated from each other, while the negative charges are separated from each other as well. We know that's not true, and we prove this wrong in the next guy with Rutherford. We know that we have a central positive nucleus. So all those positive charges are together. If you want to know why those positive charges aren't repelling each other, come talk to me, and I'll explain that to you as well. And we also know that the negative charges are not quite together, but they're definitely not mixed in with the positive charges. They're all kind of there. I didn't draw the orbitals or anything like that, so don't make fun of my drawing. But that's what it looks like. They're not all mixed together like you would think they would be. It's a small, dense, positively charged nucleus. So it is false. And I want you to write down why in your own words. Okay, so this next guy, this is one of the most important things on this video. You've got to know Ernest Rutherford. And then you've got to know this gold foil experiment. You should memorize this slide, take a picture of it if you need to, but I'll be quizzing you guys about this a lot verbally throughout class until everybody can tell us to me. Okay, so what was Ernest Rutherford's proposition? He said that the atom is mostly space, and that all of the positive charge is located in a very small central nucleus. So what he's saying is that Thompson's plum pudding model was wrong. We already know that this is true because I already told you it was true in the last slide. So what were the results of the gold foil experiment? Well, what happens here is this little thing has what's called alpha particles. So an alpha particle is a helium nucleus. So it's shooting helium at this gold foil. Now what's happening is that most of the helium goes through and hits right here. So most of them go right through the gold foil, telling us that there's nothing in the way to deflect those very tiny helium molecules. But they all didn't go through. They were ricocheted all throughout, and some actually went straight back, which tells us that at certain points there's something there to deflect that helium, but most of the time it's not there. So because of that, he makes up these three results. Most particles went through, which is what was expected, because he says the atom is mostly space. So we'll write that there, mostly space. Some were slightly deflected. That's because of the small positive nucleus. And some were deflected back and missed the fluorescent screen. So they hit it square on, came right back, and missed the screen. Great. So why are some of the particles deflected? Because they hit that small, dense atom. And you can see this up here, but if we're shooting it right here, it's going to hit this part and deflect. Most of these go right through the nuclei. I guess you can't see what I'm doing. Most of them go right through the nuclei. Some hit a gold nuclei and get deflected. Some come straight at it, hit the nuclei, and get deflected straight back. That's what's happening. So here's the video. Watch the video. Oops. There we go. Positive particles getting the positive nucleus. Pause it, read it, write it down if you want. But yeah, what this shows is the negative electrons are moving around the nucleus. They're not part of the nucleus like the plum pudding model said.
The nucleus of an atom was first discovered when a beam of positively charged particles emitted from a radioactive source was aimed at a fluorescent screen. The particles caused the fluorescent screen to glow. When a very thin sheet of gold foil was placed in the pathway of the particle beam, a few particles were deflected to the side. Occasionally, particles were deflected straight back. But nearly all particles passed right through the gold foil, as if it were not there. The scientists concluded that atoms must be mostly empty space, and that because some particles are deflected, there must be a small positively charged central mass, which they called the nucleus.
There you go. That video kind of explains it in better words, a little bit more simply than I can, but you know, that's a great explanation of it. Let's move on to our last and final scientist, Niels Bohr. The first thing he proposed was that electrons were in different energy levels. The further an electron was from the nucleus, the higher its energy. That turns out to be true. We talk more about those in Unit 5, and we'll show you what those different energy levels look like. But don't worry about that right now. Just know that they are in different energy levels. He also proposed the planetary model of the atom, which electrons orbit the nucleus, much the same way the sun. That sounds right, and we use it as a picture a lot because it's a cool picture, but unfortunately that is not the way it works. They actually work in these little tiny spheres. If you want more information about that, come talk to me about class, and I'll show you a little bit different, better example of that. So that's all we got. I know it's a lot, but you got to know what these guys did.